Thank you, Jerry, for the kind introduction and the invitation. Good morning, everyone. My name is Liang Zhang. I come from FONSAM and SWC of Soochow University. So today I will mainly talk about the in-situ Operando XAS for energy storage materials with a focus mainly on rechargeable batteries. So before the main talk, please allow me to give a brief introduction about our SWC Center. So the full name of the SWC is Soochow University Western University Center for Synchrotron Radiation Research. So Professor T.K. Shen from Western University is the director, and Professor Jeff Sun and Professor Zhong Jun are the associate director and assistant director respectively. So actually this is the first research center in China with a focus mainly on the development and application of synchrotron radiation techniques. So sorry, some problem with my presentation. Okay. Anyway, so the goal of this center is to be a global leader in the interdisciplinary research and education in synchrotron radiation research area. In addition, we all the Soochow University and the Western University want to facilitate exchange and collaborative research and education between these two universities in the research area of synchrotron radiation. So we have already carried out quite a lot of research for the center, and the main research directions of this center is synchrotron radiation study of the nanomaterials and the devices, and also energy and environment related materials and issues. We also investigate the polymer and the macromolecules, and also in the biomedical research. In addition, we also try to develop the new novel synchrotron radiation techniques. We also have some people work on the calculation about the synchrotron radiation, especially for the spectroscopy and some other related area. At the moment, there are 21 PIs from Soochow University side, and here people work not only on experiment but also the serial part. And for the Western team, at the moment there are 20 PIs, and people work on different research areas, including material science, chemistry, and physics, and also the biology. So as I mentioned, our center also tried to develop some new synchrotron radiation capability. Therefore, starting from 2014, I think, we plan to build a new beamline at the Hefei light source, and this beamline is mainly used for the in-situ soft XAS study for energy-related materials. So the energy range for this beamline is between 100 and 1000 eV. The resolution is about 2000 at 244 eV, and the flux is 5 by 10 to 10 photons per second. And this bending magnet beamline, and also for the Hefei light source, actually is a second generation synchrotron, so the flux is not very high. And at the moment, the Hefei light source is planning to build a new fourth generation light source. And actually the beamline was planned to open to users this summer. However, due to the influenza coronavirus, so we postponed the schedule to maybe the end of this year. And we are also developing some in-situ capability for this beamline, such as liquid cell and gas cell, and we plan to use this beamline to investigate the gas solid and the liquid solid interface that are related to energy materials. For example, like the lithium-ion battery, sodium-ion battery, and also some electrocatalyst. At the moment, we already get the beam from we already have the beam in the beamline, and we already measure the gas phase for the argon of the beamline. But the beam size is not optimized, and that's what we are planning to do in the following days. So in addition to the soft beamline, we also recently ordered the lab-based XAFS and XES. The energy range for the lab-based XAF is between 5 keV to 12 keV. So this equipment can be used to measure the kh of the 3D methods, which perfect for the battery research. And by using this equipment, we can also develop some in-situ operando cells to investigate the reaction mechanism of the lithium and the related batteries under the real operation conditions. So this paper published by Jerry, so they used this lab-based XAF to investigate the typical NMC electrode for lithium-ion batteries. So this is the brief introduction about the SWC Center. And so now let's come back to my own research. So for my research, I mainly focus on the application of synchrotron radiation techniques in the energy materials, mainly focus with a focus mainly on catalysts, lithium, sodium, sulfur battery, lithium, sodium ion batteries. Actually, I joined the Soochow University at the beginning of 2019. So today, the top quite a lot of the data I shown today were performed at Berkeley, at AS at the Berkeley lab when I was a postdoc there. So this is outline for my talk today. So the first part is Operando XAS for lithium-sulfur battery. So I will use two examples to show you the application of Operando XAS in lithium-sulfur battery. The first is reaction mechanism of lithium sulfide electrode. The second example is the influence of polymer binder on polysulfide Soochow effect in lithium-sulfur batteries. In the second part, I will use two examples to show the Operando XAS in lithium-ion battery, mainly about the metal sulfide electrode for lithium-ion battery. So if it's time allowed, I will also show you some new actually method for sodium-ion battery. The last part is summary. All right, so the first part is Operando XAS for lithium battery. So why are we interested in lithium-sulfur batteries? So as we all know, energy storage will be more important in the future. So at the moment, lithium batteries is playing a very important role, and the lithium-ion battery is dominating the market at the moment. However, for lithium-ion batteries, there's some drawbacks. Even with fully development, the high capacity that lithium can deliver is still too low to meet or increasing demand. In contrast, for lithium-sulfur battery, we can see here, it can deliver a much higher capacity. For example, for Nissan Leaf, the car Nissan Leaf using lithium-ion battery, it can run like 160 kilometer per charge. If we change the lithium-ion battery to lithium-sulfur batteries, the value will be increased to more than 400 kilometers. In addition, the sulfur has the advantage of low cost, nature abundance, and environment benignet. For example, for lithium-ion battery, the most expensive part is the cathode. For lithium-sulfur battery, because sulfur is used as a cathode material, the price is pretty low. Therefore, the overall price of the lithium-sulfur battery is around half of that lithium-ion battery. Therefore, lithium-sulfur battery is a very promising energy storage system for the next generation system. So for typical lithium-sulfur batteries, the sulfur is usually used as the cathode material, and the lithium metal is used as the anode material. There are also the electrolyte and polymer binder and the carbon active in the batteries. So during the discharge process, because we start from the elemental sulfur, the sulfur will first be reduced to high order polysulfide, and then to the short order polysulfide, and then finally to lithium sulfide. During the charge process, the reaction path is reversed, which means the lithium sulfide is first converted to the polysulfide and then to elemental sulfur. So although lithium-sulfur battery is very promising, there are some challenges. For example, the low conductivity of the sulfur and the lithium sulfide, and the mechanical degradation of sulfur during the discharge and charge process. In addition, the intermediate lithium sulfide has a very high solubility in the electrolyte, which can induce the so-called polysulfide shuttle effect, which is not good for the cycling performance of lithium-sulfur battery. In addition, for the lithium-sulfur battery, we use the lithium metal as an anode. Therefore, the lithium can form the lithium dendrite, which can induce a shortcut of the lithium-sulfur batteries. And during the past, like more than 10 years, people have developed different methods to overcome these challenges. So, for example, we can encapsulate the electrode with a conductive material such as a conductive binder. We can also use lithium sulfide as a cathode, because for lithium sulfide is fully licit, it's not necessary to use lithium metal as an anode anymore. We can use some other anode material such as silicon, tin, and even carbon. So, however, when we use lithium sulfide as a cathode material for lithium sulfur batteries, we always need to set a very high cutoff voltage for the first charge process. For example, this is the charge discharge voltage profile for the commercial lithium sulfur battery. Here we can see in the first charge process, the cutoff voltage is around 4 volt, which is much higher than the conventional value 2.8 or 3 watt. And during the following discharge charge process, the voltage profile become very similar to that of the normal sulfur electrode. And the CV result is consistent with the discharge charge voltage profiles. We can see in the first cycle, there's 2 ignition peaks above 2.5 volt. And in the following cycles, the peak shift to the lower voltage. So this result clearly indicates the different reaction mechanism for the first and the following cycles. And previously, people have mainly used the in-situ method to understand the different behavior, and the significant progress has been achieved. However, considering the high sensitivity of the cyclic electrode, the in-situ results are not always very reliable. Therefore, in-situ and operando experiment is very necessary to get a comprehensive understanding of the charge composition mechanism of lithium sulfide electrode. Therefore, we use the in-situ operando XAS to investigate the reaction mechanism of lithium sulfide electrode. Here we use a very simple chemical method to synthesize the nano-sized lithium sulfide materials. We can see the shape is the round shape, and with the average particle size around the 500 nanometer. And the cycling performance is not pretty good, but it's okay. So after 100 circles, the capacity is still more than 800 milliampere hour per gram. And the right figure shows the CV results for the lithium sulfide material, and the curves are very similar to that of the commercial lithium sulfide. And these results again indicates the different reaction mechanism for the first and the following charge processes. So we designed a very simple electrochemical cell to perform the in-situ operando XAS experiment. So here we use a laser to drill a hole on the cathode cap, and because we cannot use the copper current collector, here we use a carbon paper, because we mainly measure the sulfur cage, and the penetration depth of the sulfur cage is not very high. And we measure the fluorescence signal for the sulfur cage, and during the cycling process, we simultaneously record the XAS spectra. So before the in-situ experiment, we first measure the reference spectra for different kind of sulfur species. We measure the elemental sulfur, lithium sulfide, lithium polysulfide, lithium sulfide, and we also measure the lithium sulfide in the in-situ cell. We can clearly see that for the lithium sulfide, the purple line, besides the main feature, we can see a pre-age feature here, and the pre-age feature is related to the sulfur bonded with lithium in the polysulfide. And by using this pre-age feature, we can distinguish the sulfur and the lithium polysulfide. For lithium sulfide, the spectrum is very different from that of the elemental sulfur and lithium polysulfide. This is because for lithium sulfide is an ionic crystal, the crystal structure is very different from the elemental sulfur. One interesting thing is that for the lithium sulfide in the in-situ cell, besides the main feature lithium sulfide, we also find two new features at higher photon energy. So we propose this feature to be related to the oxidation of the lithium sulfide when contacting with the electrolyte. So to confirm this, we also measure the lithium sulfide contacting with different lithium salt, including lithium perchlorate, lithium nitrate, and LiPF6, and also the LiTFSI. We always find the oxidation peaks, and with the lithium perchlorate, it shows the strongest oxidation peak, and this indicating the lithium perchlorate has the strongest oxidation ability. So from this result, we can clearly see that the different sulfur species can be well distinguished by the sulfur cage XAS. We therefore perform the in-situ sulfur cage XAS. So this is the results for the first charge process, and from bottom to the top is the charge process. We can clearly see there's a very apparent change for the main feature, and its intensity is gradually increasing. However, we didn't find any pre-age feature related to the lithium polysulfide, which should be around at 2470 EV. So this result indicates that during the first charge process, no lithium polysulfide is formed. In addition, we find isospecific point for the stack plot of sulfur cage spectra. This result indicates for the first charge process is like a two-phase conversion reaction. So by using a linear combination method, we can directly derive the content of lithium sulfide and sulfur as a function of state or charge. The black curve is the lithium sulfide, and the red curve is the sulfur. We can clearly see that the content of lithium sulfide are gradually decreasing and the sulfur is increasing. So these results clearly indicate for the first charge process is a solid to solid reaction without the formation of the lithium polysulfide. Because lithium sulfide is like ionic crystal, it's very difficult to extract the lithium from lithium sulfide. Therefore, for the first charge process, a high cutoff voltage is always necessary. So we also use the same method to record the sulfur cage for the second charge process. We can see the intensity of the main feature also increases, but the intriguing thing, we can find the lithium polysulfide feature even at the very beginning spectrum. This result clearly indicates the involvement of the lithium polysulfide in the second charge process. In addition, the stack plot didn't show the isospecific point. This indicates for the second charge process is not a two-phase conversion reaction. So because for the lithium polysulfide and the elemental sulfur, the main feature is overlapped, we cannot distinguish the elemental sulfur from lithium polysulfide. Therefore, we use the area ratio between the neutral sulfur and the charged sulfur in polysulfide as a proxy of the average length of the polysulfide. We can see here the area ratio, it doesn't change very much at the beginning and then increase fast. So because there's a linear relationship between the area ratio and the average length of the polysulfide, so we can directly convert the area ratio to the average length of the polysulfide. So the right figure shows the average length of the polysulfide at a different state of the charge. So at the beginning of the second charge process, the average length of the polysulfide is around 5, which means the lithium polysulfide, the average lithium polysulfide is like Li2S5. So this clearly indicates the presence of the lithium polysulfide at the beginning of the second charge process. So because the presence of lithium polysulfide, two reactions can happen simultaneously. One is the electrochemical reaction, which can result in the increase of the average length of lithium polysulfide. The second is the chemical reaction, which can result in the decrease of the average length of the polysulfide. So these two reactions come to a balance at the beginning of the second charge process. Therefore, the average length of the polysulfide doesn't change very much at the beginning. So with the charge process going on, the electrochemical reaction becomes dominant. Therefore, the average length of the polysulfide increases. So these results clearly indicates for the second charge process is not a two-phase conversion reaction, but a solid to liquid to solid reaction, which means lithium sulfide is first converted to polysulfide and then to elemental sulfur. But the question is, where does the polysulfide come from at the beginning of the second charge process? Because in the first charge process, there's no polysulfide. So to understand this, we also record the sulfur catch spectra during the first discharge process. We can see here the intensity of main feature decrease during the discharge process. In addition, the pre-age feature related to the polysulfide start to appear, and it has the highest intensity in the intermediate discharge process. So this is the intensity of the polysulfide and the lithium sulfide as a function of the capacity. We can see the intensity of the polysulfide, the radical increase at the beginning and then slightly decrease. This indicates the sulfur is first converted to the lithium polysulfide and then to the lithium sulfide. This is also confirmed by the increase of the intensity of the lithium sulfide. So we also calculate the average length of the polysulfide using method I mentioned above. We can see here at the beginning, the average length of polysulfide drops very fast and then come to an almost constant value. This also indicates at the beginning, the electrochemical reaction is dominant with the formation of the lithium polysulfide in the intermediate discharge process. The electrochemical reaction and the chemical reaction can both happen, and these two reactions come to a balance, and therefore the intensity, the average length of polysulfide doesn't change very much. And at the end of the discharge process, the average length of the polysulfide is around 5. This indicates that the polysulfide at the end of the first discharge is not fully converted to the lithium sulfide. So based on all the results above, we can clearly see that we can get a clear picture of the charge mechanism of lithium sulfide. So for the first charge process, the lithium sulfide is directly converted to the elemental sulfur without the formation of the lithium polysulfide. In the first discharge process, the elemental sulfur is first converted to the lithium sulfide, polysulfide, and then to lithium sulfide. At the end of the first discharge process, not all the lithium polysulfide is converted to the lithium sulfide, and therefore in the second charge process, the lithium sulfide is first converted to the lithium polysulfide and then to elemental sulfur. So the most important conclusion of this research is that the polysulfide can result in the different charge mechanism for the first and the following charge process. So actually, the lithium polysulfide can not only influence the cathode but also the anode. For example, the lithium polysulfide can react with the lithium nitrate to inhibit the formation of lithium dendrite. We also perform the in-situ XAS experiment. We perform that the lithium nitrate and the polysulfide can react to form a protection layer on the lithium surface. The layer is mainly composed of the lithium sulfate and sulfide, and this layer can stop the reaction between the polysulfide and lithium metal. In addition, the concentration of the lithium polysulfide can also influence the cycling performance. If the concentration of the polysulfide is too high or too low, it cannot form a complete protection layer on the lithium anode. So the question is there any method that we can control the dissolution of the lithium polysulfide in the electrolyte? And the answer is yes. If we look at the structure of lithium-sulfur battery, one very important component is the polymer binder, which is used to glue the sulfur particle and the carbon additive. For the commercial binder, we usually use PVDF. However, for PVDF, it's like a chemical interaction with the lithium polysulfide. Therefore, it cannot prevent the dissolution of the polysulfide. So here we propose to use polyethylene and PEI for short as the polymer binder. The advantage of the PEI binder is it has abundant of the nitrogen containing functional group. It also has a branched structure, which can provide a very strong affinity to the polysulfide. So this is the cycling performance for the PEI binder. We compare with the commercial PVDF binder. We can clearly see the cycling performance is greatly improved by using the PEI binder. To demonstrate the strong interaction between polysulfide and the PEI binder, so we first perform the in-situ UV-Vis experiment. The left is the PEI results, the right is the PVDF result. We can clearly see the feature of the lithium polysulfide is continuously decreased in 10 hours, while for the PVDF, the intensity doesn't change. In addition, we can also see for PEI binder, the typical yellow-gold color of the polysulfide becomes almost transparent after 24 hours. So this result clearly indicates the PEI binder has a very strong absorption ability towards polysulfide. To further demonstrate the strong interaction between PEI binder and the polysulfide, we also perform the in-situ experiment. Here we use a specifically designed in-situ cell. We can directly detect the sulfur signal in the electrolyte. So the left is a counter plot for the sulfur cage results, and the X is the photon energy, the Y is the state of charge. The different color indicates a different intensity. The right figure shows the several typical spectra. So for the PVDF results, we get the similar results, and we can clearly see the increase or the intensity of the polysulfide during the discharge process. However, if we plot the intensity of the polysulfide for the PEI and the PVDF binder, we can clearly see the difference. For the PVDF binder, we can clearly see the continuously increase of the polysulfide intensity, which indicates the sulfur is first converted to the polysulfide, and the polysulfide is easily dissolved in the electrolyte. However, for the PEI binder, we can see the intensity is increasing initially and then slightly decrease. This indicates that part of the polysulfide can still be dissolved in the electrolyte, but at the end of the discharge, part of the polysulfide is converted to the lithium sulfide. So the XAS result here provide a very direct evidence for the surprise of the shuttle effect for the lithium sulfur battery. Okay, so this is the first part of the results. So
great start. Thank you. That's very interesting. First, a general question. I understand that your motivation for lithium-sulfur batteries is for transportation, but what is the present status of commercialization of lithium-sulfur batteries? What are they used for now?
Actually, for lithium-sulfur battery, it's difficult for the transportation because the energy density total is not very high, because you can see the average is pretty low. Is for sulfur is around 2 watt, so much lower than the lithium-ion battery. Actually, the advantage is for the lithium battery is can deliver very high specific capacity within one charge. So if we use like only for one in a special situation, we can use it, but for transportation it's difficult. But considering the status of lithium-sulfur battery, and at the moment actually it's kind of difficult to further improve the capacity, because now we can achieve to like around 1100 milliampere-hour per gram, and the theoretical value is around 1600 milliampere. But at the moment for the lithium-sulfur, the loading, I mean the loading of the per square centimeter is pretty low, and we are trying to increase the loading of sulfur battery.
I understand. Is there an application in the world right now that uses lithium-sulfur batteries, or is this right now just a laboratory battery?
As far as I know, there are several companies work on the lithium-sulfur battery, but I don't know if there's any real application for lithium battery. I know there's some project from the U.S. Army. Maybe in the U.S. Army they are using for the very specific purpose, but for the commercial lithium, as far as I know, it seems no real application.
All right, very good. Carolyn, you had a question?
Thanks, Liang. It's like incredibly interesting work, and the way that you set up the cells is really neat. I was just wondering about sort of fitting the spectrum, and I think it fits into the questions that Matt are going to ask. But do you do any modeling of the spectra, like time-dependent DFT analysis, or do you collaborate with people on that, on the modeling of the sulfur spectra?
No, we didn't do any modeling for that. Actually, before that, I just discussed with Jerry. Actually, at the moment in the world, there are not so many people work on the modeling sulfur cage. And I think in Jerry group, they are doing some theoretical calculation for the sulfur cage, right, Jerry?
Yeah, but it's very early. What we learned is that it's not easy to decide which code to use for sulfur. At lower and higher energies, it's maybe a little bit easier. But there may well be a real expert about that who can correct us, and then we can all learn during this talk. Yeah. Did you want to follow up, Carolyn?
Thank you. No, I think there's like a lot of potential for collaborating on this, and with NERI just had the sulfur XAS paper published, so there's been big strides in the sulfur modeling community. So hopefully there's more to come.
Yeah, for the modeling, I think it's very useful, because I also have quite a lot of unpublished sulfur cage results, because we don't know how to explain it.
Okay. Matthew Marcus, you had a question about principal component analysis?
Yeah, and the second charge process that you have up now, I was wondering if you did PCA and whether 3 components sufficed.
We didn't do this for the second charge process, because actually you can see that the quality of data is not very good. We can still, it's kind of noisy. I don't know if by using the PCA, if we can get some reliable results or not.
Yeah, I participated. Some years ago, I worked with with Jinghua Guo and some other people on some lithium-sulfur stuff, and we use PCA. But,
oh, okay. Yeah. I read that paper.
Yeah, that had theoretical analysis in it.
Yeah, because for the data here, I collect on the at beamline 5 at AS. I don't know why, but we can always not get a very high signal to noise ratio results.
Beamline 5, is that
531? 3-1. Yeah.
Yeah.
I don't know why, because at your on the at beamline 10. I didn't do the in-situ experiment on your beamline 10, but I measured some ex-situ results, but I can always get a very beautiful sulfur catch results.
Yeah.
I don't know
right. I'm not on that beamline anymore, but Serene Fokker runs it now, and she gets beautiful sulfur data.
Okay. Yeah.
Okay, very good. Kevin, you have a question?
Yeah, hi, Liang. Really nice. This is Kevin Rosso. I'm curious about the Li2S crystal structure possibilities versus an amorphous structure. And if you've evaluated this difference, and if you get a potential, a battery voltage difference associated with the structure difference, I would suspect you would.
Actually, for the initial lithium sulfide, we measure the XRD. It has a crystal structure. But actually, after circling, it seems that because we also measure sample for the Li2S after cycling, it seems that all the differential peaks disappear. It seems it's become too amorphous even after only one cycling. So we don't know the reason for that.
Yeah. So in natural sulfides, it's pretty typical as you go from crystalline sulfides to something in solution, let's call it electrolyte, that you would go through polysulfide. So the fact that you see polysulfide as an intermediate kind of suggests to me that you've got maybe some higher crystalline order in your Li2S. So it's kind of interesting to know what that is.
Okay, yeah, that would be interesting. But the thing is, actually, I discussed the data with some other people, because for the XAS, it takes around 15 minutes to one spectrum. It seems because in addition for the conversion, the lithium polysulfide is very complex. It's maybe mainly the issue, the time scale. It's how fast it converted from one to another.
Okay. Yeah. Yeah, it's very nice. Very interesting.
Yeah, thank you.
All right, you should continue, Liang. We're running a little bit late, so you should continue, please.
Okay, yeah, I will be a little faster. Okay, let's see. Okay, so the second part is the Operando XAS lithium-ion battery. So at the moment for lithium-ion battery, we mainly use graphite. However, for the graphite, its capacity is only 372 milliampere hour per gram. Therefore, people are trying to develop different anode material for lithium-ion battery. So among the different, including the metal oxide, metal sulfide, and metal nitride. So among these materials, metal sulfide electrode attract intensive attention, mainly because the advantage of low cost, controllable morphology, and high theoretical capacity. However, for metal sulfide, they also have some disadvantage, including the short lifetime, very fast capacity degradation, and especially for the reaction mechanism, it's still controversial. So therefore, we first investigate the very common electrode named moly-sulfide. So during the lithiation process, it mainly have two reactions. The first is intercalation reaction. The second is conversion reaction. So for the intercalation reaction is very reversible. For the conversion reaction with the lithium sulfide and the moly metal as the final product, reversibility of this conversion reaction is still not very clear. So therefore, we use the sulfur cage XAS to investigate the reaction mechanism of the moly sulfide. So this is intercalation reaction results. So here, I showed the counterplot with X is photo energy, Y is the state of charge, and here the different color indicate the different intensity. So the spectral shape doesn't change very much during the charge and discharge process. And to further analyze this data, we plot the intensity as the main feature in the sulfur cage results. And we also compare the in-situ results with the ex-situ results. Here the blue curves are the in-situ results, and the red, are the ex-situ results. We can see here, it seems that the lithiation degree is always higher for the ex-situ results. So to understand this, we perform some simple DFT calculation. We can see for the lithiation can induce the phase transition of moly sulfide from 2H to 1T. And for both 2H and 1T phases, they are semiconductors with a band gap of the 1 eV. So because of this, the in-situ, it seems that the in-situ results are not relaxed for the moly sulfide. Therefore, the lithiation degree is always lower compared with the ex-situ results, because for ex-situ results, they have enough relaxed time. So we further investigate the conversion reaction for the moly sulfide. Again, the upper are the in-situ results with the counterplot, and the bottom are the left is the ex-situ, the in-situ spectra, the right and the ex-situ results. From the results we can see, from the ex-situ results we can clearly see the conversion from moly sulfide to lithium sulfide at the end of the discharge, because the spectral shape is very similar to that of the lithium sulfide. During the following charge process, the structure of moly sulfide is not recovered, but the spectra looks very like to that of the sulfur. This indicates the conversion reaction of the moly sulfide is not reversible. But here, the in-situ results are actually quite different. So this is mainly because for the in-situ results, we continuously record XAS when cycling. So the moly sulfide electrode don't have enough relaxation time. And further, the lithium sulfide and sulfur are insulators. So this can result some sluggish kinetics of the electrode. And we also use the DFT calculation to confirm that there's a strong interaction between the lithium polysulfide and the metallic moly, because this strong interaction can prohibit the dissolution of the polysulfide in the electrolyte. This is confirmed by the experiment here. For the second electrode, we didn't see any color change for the electrolyte, because the polysulfide in the electrolyte has a golden yellow color. So here we can see the electrolyte is still transparent. This indicates a strong interaction between the moly and the lithium polysulfide. So the bottom picture shows the conclusion of all experiment. For the intercalation reaction is reversible with the phase transition from 2H to 1T. Sorry. For the conversion reaction is not reversible. The final discharge product is the lithium sulfide and moly, and during the following charge process, the lithium sulfide is converted to the sulfur, and the moly sulfide structure is not recovered. So for the moly sulfide, it has 2 sulfur in each unit. If we increase the content of the sulfur in the unit, in principle, we can increase the capacity. Therefore, we designed the material VS4 and investigated the reaction mechanism, and the XPS, XRD results and SEM indicate the successful preparation of this material. So different from moly sulfide, so VS4 has a linear structure, and the chain distance is 0.58 nanometer, and it also has two reactions during the lithiation. One is the intercalation reaction, one is a conversion reaction. Here we again investigate the reversibility of the conversion reaction. So here we mainly measure the sulfur KH and the vanadium KH spectra. The left are the sulfur KH results. The upper is the discharge results. The bottom are the charge process. So here for the sulfur KH spectra, the main feature look at the 2471 EV. This feature is the hybridization between sulfur 3p and vanadium 3d states. And during the discharge process, the intensity of this feature gradually decrease. And at the end of the discharge process, the spectrum is very similar to that of the lithium sulfide, indicating the conversion from VS4 to lithium sulfide. And during the following charge process, the main feature is partially recovered, indicating the partial reversibility of the conversion reaction. This is also confirmed by the vanadium KH results. The pre-age feature is related to the 1s to 3d transition. And during the discharge process, the pre-age feature gradually disappears. And in addition, the main absorption age shifted to lower binding energy, indicating the reduction of vanadium. During the following charge process, the pre-age feature is reformed, and the main absorption age gradually shifted to the high binding energy. So this result clearly indicates that for the conversion reaction on vanadium sulfide is partially reversible with lithium sulfide and metallic vanadium as a final reaction product. So this is the second product. So because the time issue, so I will skip the third part. Let's move to the the summary. So I hope I have shown you the application of the in-situ Operando XAS in battery related research. So in the first part, I showed you two different examples. One is the reaction mechanism of lithium sulfide. The second is the inference polymer binder for suppressing the polysulfide shuttle effect. And in the second part, we use the sulfur KH and metal KH, 3D metal KH to understand the reversibility of the conversion reaction moly sulfide. So that's the summary. So finally, I would like to thank the Professor Li from Fosam and also TK Shen from Western University, and also my postdoc supervisor, Dr. Jinghua Guo. And I also would like to thank the funding support from NSFC and the SWC. And thank you for your attention.
Very interesting. First, there was a question about that the molybdenum L3 edge is a little bit above the sulfur K edge. And someone was curious if you've ever included the molybdenum L3 edge in your study of the moly sulfide.
Actually, I measured the moly L edge, but I don't know why, but the intensity of moly is always pretty low, and the single to noise ratio is pretty bad. So I didn't show the data. But we can see the edge shift. We can see the edge shift in the results.
I see. Very interesting. I have to admit, when you were flipping through the slides at the end that you wanted to skip, did it say something about developing Rick's capability? Would you like to spend a minute telling us about that?
I didn't develop this, but the Wan Li and Yide and Jinghua at AS, they developed this technique. I only use this technique. So it's mainly about recently Wan Li at AS, they use the Rick's map to investigate the oxygen redox in the transition metal oxide electrode for lithium and ion battery. They got very beautiful data. I only use it to measure the 1 or 2 system. But Wally and Jinghua and Yi-De, they are experts in this area.
Very good. What do you see as the spectroscopic challenges that you would most like to overcome in these sulfur-rich materials?
So, sorry? What?
You've learned a lot about the sulfur redox cycling.
Yeah,
Is
yeah.
there some limitation in the spectroscopy that you would like to get past? Whether you need more flux or more focusing, or you need RICs, well, what would make your science stronger?
One thing is so if possible, I want to measure the time result sulfur cage, because the redox reaction sometimes very fast, and at the moment each spectra takes about 15 minutes. Maybe some reaction has already happened in this time period. If we can, I don't know if the flame mode of sulfur cage can be realized, it would be much better. Maybe, for example, if we can take one spectrum in the time scale the seconds, it would be much great. The second challenge is the explanation of the sulfur cage. Actually, we got quite a lot of sulfur cage results, but the question is how to explain the spectral shape change. If we can combine the experiment results with simulation, that would also be very useful. And the third is because for the sulfur cage AS, we can only get the unoccupied state. If we can combine the XAS with XES, then we can get both the conduction band and the valence band, the electronic structures. I guess we should be able to get more useful information.